And we're good to go. Celeste, floor is yours.
Okay. Okay. So I hope you guys were able to find the photos of the questions I sent. I sent about 5, though the last one haikufanywa vizuri, but yeah, we'll go through them. So I'll try and explain very well as much as possible using questions. If you have any question, you can unmute your mic and ask. Na kama ndapita haraka na uelewi, you can just ask so that you understand. Okay. So most of the questions, I did a very short summary. We're going to be talking about differential amplifiers in most of these ones. And a few points you should note. We are going to be dealing with either double-ended input, double-ended output, double-ended input, single-ended output. At least for the questions I've done, hizo ndio nimepata. So, okay, let me just give you a quick example of what we are, like this one. If you check here, we have 2 inputs. We have an input here and here, and we have output here and here. So this one is double-ended input, double-ended output, as Bill calls it, DIDO. And then here, check here, we have 2 inputs. There's one here, there's another one here, and there's one output. So this is a double-ended input and a single-ended output because you're only taking output from one point. And the formula...
question.
Yes.
For the double-ended input, for these amplifiers, the only difference is where we're taking the output or also the resistor placement.
Also the resistor placement.
Yeah, so for the double-ended input, double-ended output.
For example, let me give you... Okay. Yeah, so here we have a double-ended input and a double-ended output. So unaona penye kuna output, there are resistors. These RC. But here, where we have double-ended input, so 2 inputs, and we have 1 output, the resistor is only on the output side. Sawa?
Nice, thank you.
Cool. Sawa, so let's start. So the thing I wanted you to realize is the formula for the gain. So the voltage gain for DIDO, it's RC over RE. So I'll show you how to do this. And for the double-ended input and single-ended output, it is RC over 2RE. Another key point is knowing what current mirror principle is. So this is something we'll look about.
In the previous, is the input impedance also different for the two? Or it doesn't apply on the questions which he usually sets?
Okay. It is the same. Actually, it is the same. We'll do a couple of questions and you'll realize it's the same.
Nice. Thank you.
Okay. So another key point is current mirror. So I've really summarized it here. I've said when the emitter has the same voltage. So if you have 2 transistors and the emitters have the same voltage, and also the base, so you see the bases are joined, have the same voltage, then the collectors will be the same. So ni kama collector current hapa, it's being mirrored here. So this is something you also have to note. So yeah.
A question, Celestine. Does it, there's the problem that sometimes confuses me. When there's a resistor on one of the collectors, does it affect the current mirror or will the current mirror remain the same?
If there's a resistor in one of the collectors.
Yeah, on one of the collectors, but not the other one.
It will remain the same.
Nice, thank you.
Okay. So there's another key point. So this is the last bit I'm going through in summary. So you'll see questions that ask you or give you maximum peak-to-peak voltage swing. So the reason they give you this is for you to be able to calculate VC. And normally we say VC must be more than half the maximum peak-to-peak voltage to prevent clipping. So, for example, if you're told our maximum peak-to-peak voltage swing is 10, it means that our VC will be half, so 10 divided by 2 plus 1. So VC has to be more than half the maximum. So itakuwa 10, which is maximum voltage peak to peak, over 2 plus 1. Aya. Are we good till there?
Yeah, I
Wait,
have a
wait,
question.
wait. Okay, Bill, go ahead.
Yeah.
Yes.
The question is, is there a reason why we can't make it a very large value?
Yes. Oh God. Hii kitu nitaipata wapi? It was, there was something, okay, it's somewhere in my notes. Yeah. So you were saying that, no, wait, you're asking the value of VC, Bill?
Yes, the limitation of not making VC too large. Like, why can't you say it becomes 10 volts or, yeah.
I read it somewhere, but I don't remember.
Oh, it's okay, we'll get back to it.
Okay, we'll get back to that. Sawa. Yes, Fiona?
I think ilinipita kidogo. You said 10 over 2 plus 1.
Yes.
Why is plus 1? Or that's just the lowest we can get for this?
Yes, that is the least. So we are saying if you're given your maximum peak-to-peak voltage swing is 10, Cindy. For you to calculate VC, it must be more than half the maximum peak-to-peak voltage to prevent clipping. So normally, okay, you can have, half is 5, yeah? So you can have, so more than half, more than 5 is plus 1 and above. So I can say this is the least VC you can have for this particular setup for clipping, not to occur.
Okay.
So let's start on questions. So I hope you guys were able to access the photos I sent on the group ili tuende haraka. So
Celeste,
yes.
ambia Bill, VC haina limit. VC can be higher to the maximum to the supply, but it should not be lower to the point in it is less than half.
Okay, Bill, are you listening?
Yes, thank you, Joseph.
Okay, I know the value for the value of RC is something that we should not set too high because it will make VC too low and it can make the transistor go into saturation. Okay, sawa. So let's start. We're going to start with this question. I hope you guys can see it well. So this is a very easy question. Ikikuja ini free marks. Now first, you have to identify what differential amplifier you're dealing with. So here we're seeing there are two inputs. So it's a double-ended input and there's one output. So double-ended input, single-ended output. So automatically by knowing that, we know that our gain, let me call it will be 2. So that is something you have to remember. So the question is saying, okay, let me tilt like that. Figure Q1, B shows a partially designed amplifier circuit with a gain of 200. The transistors used have a current gain of 125 and the value of RB is 5 kilo ohm. If the measured tail current is 2.86 milliamps, determine the power supplies. So we want to determine VCC and VEE. We want to determine the collector resistor RC, input resistance seen by Vin, and maximum voltage swing peak to peak. Okay, so let's start with the power supplies. So, here, power supply we're going to use a loop hapa because already tumeambiwa IT ni 2.86 milliamps. So this IT is what is flowing here, okay? And it's also, because you're seeing the collector and the base are joined. This is like a diode, yeah? So it's also what is flowing here. So we'll use KVL for this particular loop. Using KVL, we will have IB. So we'll have, let me call this IT, because this is tail current, IT RB plus, okay, plus VBE hapa. So VBE plus, so our loop ends here. So plus, let me say plus minus VEE. All this should be equal to 0 according to KVL. So this is how I was able to come up with this equation. Okay. So we know
Question,
our
Celestine. In that part, can you also use the reasoning that the tail current is going to be the same as the other current because of current mirror principle?
absolutely. Actually, that is the best reasoning.
Oh, thank you.
Okay. So we have VEE. Hatuna. So this is what we're looking for. We have IT. We have RB, we're told is 5 kilo ohms. Yeah. VBE, tunajua is 0.7 transistor. So if I calculate this, I find VEE is 15 and VCC is also 15. Okay, normally from the questions I've done, you'll find VEE is equals to VCC. The only difference is the sign. So make sure in your answer, kwa part ya VEE, you write it's negative 15, and VCC it's positive 15. Yeah. Anyone has a problem? Hapo tuko sawa?
Yes.
You all okay, good.
I think, Celestine, maybe you can go through that loop again, the KVL loop. I think something might have skipped me.
Okay. So let's start from here. Okay. So we've seen from current mirror, the bases have the same voltage and the emitters are also having the same voltage, which means the collector of this transistor and the collector of this transistor have the same current. So that is why this current of 2.86, the tail current, is the same current flowing through this collector. So for our KVL, we have IT RB. So tunaanzia hapa tukienda IT RB. Haya, tunakuja tunapita. So hapa tuko na VBE. Okay? Haya. After VBE, we end up hadi VEE. So I said IT RB plus VBE plus minus VEE. So don't forget about this minus VEE is equals to 0. So that is how I ended up with this particular equation.
Thank you.
Cool. So now we have already found our power supplies. Let us look for the collector resistor. Now, what will help you here is this formula.
Wait, Celestine, I have a question.
Yes.
That's part for that loop, that EVL loop.
This loop.
Yeah.
Mm-hmm.
See how the current is flowing from ground up or towards Q4.
To what?
Towards Q4.
Mm-hmm.
Into the collector for Q4. So this makes such a dumb question. But does it mean that like there's from KCL like nothing goes beyond?
Let me just nothing goes beyond what?
Like you see how the 2.6 milliamps is coming from RB going towards the left, then it all goes down into the collector. So from KCL, like, there's nothing that goes like beyond the collector. More left.
I think maybe the question might be regarding the base current
Yes.
in this question.
Mm-hmm.
Yeah, she's asking, I think, maybe why we are not taking into consideration the base current.
What do it says ignore the base currents, but also, okay, I'm not too sure about this explanation, and anyone can help me out. But I know if you join the collector, collect the collector to the base, it forms a diode. Sindio, if you short the base to the collector.
Yeah,
Sindio.
yes.
So I was just, for me, I'd say the voltage drop that would occur in this transistor, because it's now acting like a diode, would just be VBE. I'm not too sure. Does anyone have a different point of view?
Yes.
Mine on the other questions he usually asks, because they all say usually ignoring base current.
Yeah, there's also that. Yeah.
Celestine,
Yes.
it at this point it would be important to know to try and hiyo story ya current na voltage
Mm-hmm.
hapo kuna mtego because that 2.86 it does not go into the base.
Does not go
Hiyo
into the
2.86 and into the base. What you're actually looking at, that part, the only thing you're looking for is the voltage actually. So it doesn't, in fact, it doesn't even go through the collector. Inaenda inatoka from RB. When it goes to the collector, it finds that the junction between the collector and the base are reversed. So inaenda hiyo voltage inaenda inapitia through the base. That's why we are dropping VBE. We are not considering the drop between the collector and the base. We are considering the drop between the base and the emitter because there is no flow from the collector to the base.
Oh, okay.
Yeah.
Okay.
But I think also the reasoning that since the base and the collector have been shorted, so
Mm-hmm.
the voltage VC is also equal to VB.
Yeah. That's
So I
accurate.
think the same reasoning also applies there.
Okay.
Yeah.
Okay. Okay. Sweet. Thank you guys for your help. Fiona is asking why is your VEE negative? The question had a negative VEE here. Okay. So you would find your value of VEE normally, like we've done in our loop, and then attach a negative to it. Okay, I hope that answers you, Fiona.
Wait, Labda, I need some reboot. See, when we did that equation, we included the negative.
Yes. Yeah.
We did not do it as a positive.
We did not do it as a positive for sure.
Be the subject and the answer is positive. So now because it was negative before, it becomes a negative.
Um,
Or it's just like that.
Let me not just say it's just like that. But normally, for such questions and for the number of I've done, the value, let me say the magnitude of VCC, most of the it is the magnitude of VE, despite the difference in times.
Sorry, you're breaking a little bit.
Sorry, you can hear me now? Hello?
Yes.
Okay. So I'm saying the magnitude of VCC, normally, in most cases, you'll find it is equal to the magnitude of VEE. Okay. So,
Yeah, it makes sense.
yeah. So just the magnitude, but now there's a difference in signs. Okay.
Thank you.
Okay. So let's move on very quick. So want to find value of resistor RC. So we'll use this formula of ours for double-ended input, single-ended output. So I'll collect a resistor RC. Do it to formula. So first you want to find what value of RE is. So you can either use the formula VT is equals to RE is equals to VT over IE, or input impedance is equals to 2 beta RE. So this time I chose to use this particular formula. So let's go back so that you see. So we said that our transistor has a value of 2.8. Our tail current is 2.86 milliamps. This tail current, it is the sum of these two. Okay, and we normally say these two are equal. So to find the emitter for one side, it is the tail current divided by 2. So let's look at transistor 1. So this is like for the differential, this particular differential amplifier. So IE is IT divided by 2 for you to get that. Haya, mmelewa diapo?
Yes, yes.
Cool. Now, after we have that, sasa tuko na IE. VT is a fixed value. You see the way we say VBE is 0.7 volts. VT is normally 25 millivolts. So we'll have 25 millivolts over our IE we found is 1.43 milliamps. Tukapata RE yetu ni V. So we were able to find RE. We know our gain we were given is 200 in the question. So to find RC, it will be 2 times our gain of 200 times RE of 17.5 to get 7.5 kilo ohms. Are you guys fine until there?
Yeah. But then I have a late question. So now the values of RE, are we going to use for the transistor to the left or the transistor to the right?
No. The values of RE
Yeah.
is same for this amplifier. You know this one, this is like one system.
Yes.
Yeah. So the value of RE is the same. Let me just say
Oh.
whole system, it is the same. Okay.
Oh.
And we will look at one which has tuseme double-ended input, double-ended output, and it also has a double-ended input and single-ended output, and we'll see how to treat them. Okay. I hope you guys are okay. Nisipite na ujeelewa. So the next thing we want to do is to calculate the input resistance seen by V in. So this is another point I need you to be very keen about. So ukiona V in, it is here. So we want to look at the resistor that is being seen. Okay? Ni kama by the, I think, by the source. Aya. So there's a formula we normally use. We say Z in is equal to 2 beta RE. You know beta is current gain, it's already in the question. RE, we are able to calculate RE from here. Actually, it's just here, 17.5. So this one is as easy as saying 2 times 125 times 17.5 for you to get your input resistance seen by V in. No, wait. That is your input impedance. Sorry. That is your input impedance. Input resistance being seen, you know, by the source. Okay? It is going to be your input impedance times, I don't want to call it Z, need R. Okay, let me just call it Z, where Z is R. So this R, it's this one. This is what I'm calling Z. So we are saying the impedance being seen by the signal will be the input resistance in parallel with R1. So
Wait, so let me think. I have a question. Are we also going to consider the R2?
R2, where is R2?
And the other R1, yani. The one hapo, here R2 hapo actually. It's called R2. There next to transistor Q2.
No, I don't think so. Okay. I don't think. No, wait, let me check. Yes, funny nimeangalia. No, we won't.
Oh, okay. Why is that?
We won't consider y. Input. Rest are in. I'm not so sure about that. If anyone has a reason, do you have a reason, Bill?
I was also not very sure about it.
Yeah, because when we did it in class, we only considered one.
Oh, we only considered one, yeah.
So just now for safety, before we find a landing space, let's just leave it at that. But we'll research about it, of course.
Okay.
You guys, are we together? I'm seeing questions. When do you know which beta to use in a calculation? What do you mean which beta, Mike? Because here we've been told our current gain, HFE, is 125. So, oh, by the way, you guys must confuse current gain na voltage gain. Be very careful. What we are calling a D is our voltage gain, or a V, depending on what you use. Okay, Mike, I hope that answers your question. Okay. So, the input resistance, tutakuwa na Z in, hiyo yenye tumecalculate. Let me call it here. Yeah, in parallel with Z or R. So we'll have 4.375 in parallel with 100. We'll do product sum. So this times this over this plus this. And this is what you'll end up with. So, hope that's okay. Any questions from there? Okay, I think you guys are good. The last part of the question, maximum peak-to-peak voltage swing. So let's see this one. So you guys remember when I told you that the value of VC should be more than half the value of the maximum peak-to-peak voltage swing. That is what we're going to apply here. So the first thing we're going to do is to find VC. And the VC we are looking at ni VC yenye iko hapa. Because this is where we're getting our output. So VC will be VCC minus the drop here. So VCC, current hapa ni 1.43A. Yeah. Current times resistance to get VC. So our VCC, we found ilikuwa 15. So we'll have 15 volts minus the drop across the resistance, which is that, to find that our VC should be 5. Likuja kama 5 volts. Now, if our VC is 5 volts, and we know that the voltage maximum peak to peak, actually this is VC, over 2 plus 1. For me to get maximum peak to peak, senye niko na VC, first I'll minus 1. So if my VC is 5, I'll minus 1 to get 4. And then I'll multiply by 2. So I'll get my maximum voltage swing to be 4 times 2, which is 8. Any person, anyone with a problem with that? Okay, so tuko sawa.
No problem there. I think you've explained it well enough.
So I hope.
Kidogo. You see maximum V peak to peak is 4 volts, but maximum.
We said.
Okay, I understand the math. It's the wording.
The wording. Oh, okay.
I'm not understanding the wording. It's maximum peak if it's not divided, if it's not multiplied by 2. Oh, so that whole thing is okay. So I've understood.
You've understood?
Yes.
Okay. Anybody else? Okay. So this is we have done one question. We are moving on to the other one. This is a really good question. The second one we're going to do. and I hope you'll be very keen about it. So here, it's very good because we are having double input. So we have 2 inputs and 2 outputs. And then we have 2 inputs. If I hapo, this resistor is not supposed to be there. So we have 2 inputs and 1 output. So double-ended input, single-ended output.
Celeste. Sorry, can I bother you, Cassie?
Okay.
You're saying the solution to B is
2B.
is 8 volts.
Yes, it's 8 volts.
The question is, sorry.
The question was, get the maximum peak-to-peak voltage swing.
Oh, okay. Thank you.
Okay. So now we're on question 2. So first, always check kama kuna double input, double output, and then write the formula ili usisahau, usimefike mahali, and then you confuse. And then another thing I want you to note with such a question is that the total voltage gain will be this gain times this gain, because there are 2, so you multiply. Okay, so let's start. Sweet. Hope you guys are curious to know how this will turn out. In the amplifier,
Yes.
in the amplifier, the current. What is this? The base emitter surface area of
That's the
Q3
junction, the base emitter junction. I think that's
junction.
what.
Okay, I don't know what this is. Area of Q3, so transistor 3 is 2 times that of the other transistors. Given that, so I wrote the parameters here. If you're given that VEE is equals to VCC is equals to 12. So again, Fiona, on your question, even in questions teacher gives us, venye amesema VEE is equals to VCC is equals to 12. There's a positive here, but there's a negative down here. So I think it's some sort of convention he uses. And then the value of RC is that, RB is that. So what's the question? Determine nominal currents, that and that, midband and voltage gain. So V out over V in. So first let's do the nominal currents. Okay. Happy? So to do the nominal currents, you want to find the currents that are getting in. Okay, so the currents getting in ndio tunaita hivi, and the currents coming out down here on the negative side ndio tunaita hivyo. So you can start from here. So you always check the values you're given. Kama here you've been given RB, RC. So if you have RB, you can use KVL to get the current.
Okay.
Sindio? Bill?
Yeah.
You okay? You're cool, yeah?
Yeah, that's making sense. We're just going to use the same formula as last time.
We're just using the same KVL, by the way, because now we
Oh,
have I1, RB. Now we're going plus. What do I call this? Let me just call it IE3. Yeah. No, sorry, VBE plus VEE. So that is just what we're going to use. So we'll have our KVL as niandike hapi, cha niandike hapa. So KVL, we have I1 RB plus VBE plus minus VEE. So don't forget this minus. So this all should give us 0, like that. So if we have our KVL being this expression, we don't know the value of this one. We know RB, tulikuwa tumepewa. VEE tulipewa as 12. VBE is 0.7, of course. If we make I1 the subject, we end up with this expression. Yeah, so we've divided by RB on both sides. And then, yeah, we were given VEE is 12, VBE is 0.7 over RB is 11.3 kilo ohms to get our I1 as 1 milliampere. Are you guys okay till there?
Yeah, it's just like the previous one.
Exactly like the previous one.
Yeah.
We've been able to get I1. And this is our collector current here. Okay? So we will use current mirror principle.
Yeah.
If you check the base of this one and the base of this one, they have the same voltage and their emitters have the same voltage as well.
Yeah.
So the conductors have the same current.
Current.
Cool. But now remember here we've been told transistor Q3, its surface area is twice the surface area of all other transistors. So it's twice. Ndio maana tumeandika hapa times 2. So if the current here in the collector was 1, here it will be a half.
Okay.
Yeah, because of the difference in surface area. So it's a half for the tail current here. To get this current and this one is easy. Yeah, it's just going to be this tail current divided by 2.
Wait, I have a question there. Here, why are we just saying it's divided by 2 yet there is no current mirror?
Because they share equally. Okay. Let me see. Also, they are matched transistors.
Yeah.
I don't have an exact answer, but I'd say they are matched transistors.
Or maybe it could be because of the voltage is the same, and then they have the same
Exactly.
collector, everything is the same.
Yeah. So VBE here is the same, collector is the same, so emitter is also the same. So ni kama there, it is half the value of tail current.
Oh, nice.
Okay. So half of T1, so half of this one hapo utapata hapa and here. Then of course the assumption that IC is equals to IE when beta is greater than 1. So this is the same IC flowing here. You guys are good till there?
Yeah, I think so.
Okay.
Wait, I was confused with Bill's question.
With Bill's question, he was asking why this current is equals to this current.
Oh, okay.
So we are saying they're matched. Okay, they're matched transistors, yeah? So the value of VBE here is the same.
Okay.
Which means also the value of emitter current here and here is equal, and the value of collector current here and here is also equal.
Okay, so current mirror doesn't just apply to the collectors.
Current mirror doesn't apply here though. Because
Okay.
remember what we've said for current mirror, the bases must have the same voltage, okay, and the emitter voltage must be the same.
Hello.
If is also the same.
Celestine, you got
Can you hear
cut
me?
off a bit. Maybe you can repeat from where you are saying that the base voltages are the same and the emitter voltages are the same.
Yeah, so base voltages are the same, emitter voltages are the same. This makes so this is where current mirror comes and says that the collector current here is the same as the collector current here.
Tell us.
Yeah. Hello.
Why you dividing? Why are you saying IT equals to I1 over 2?
No, this is supposed to be IT. No, IT.
Hapo malume.
Aya, hapa.
Please explain hapo.
If you check in the question, we are being told that the surface area of transistor 3 is 2 times that of other transistors. Sawa. So, current mirror will apply. So hapa, we found out our I1 is 1 milliamp. But now, the surface area for this transistor, it is twice the surface area of other transistors by 2 to find this collector current.
Sasa na hiyo story ya current mirror, kama tunasema tuna apply current mirror, why are we again dividing it by 2?
We're dividing by 2 because the
Ama
areas
ni
of
your size.
yeah, because of size.
Basi hapo is current mirror principle applying.
It is a but if Waki mentioned size, you have to take size into account.
I think maybe
Here.
what can help maybe is that for current mirror, it doesn't mean that they are exactly the same. It means that for the two transistors which have the same base voltage and emitter voltage, the current through one collector is going to be related to the current through the other collector, but not always exactly the same because it depends on the base area of the, yeah.
Oh, okay. So as if I were the same.
Kama
Okay,
area ni
makes
the
sense,
same,
makes sense.
zitakuwa
Thank
the
you.
same. Exactly the same. Kama area ni the same. Kama area ni different, utafanya hiyo multiplication.
Oh, okay. Sawa, asante.
I have a question. Celeste, in this diagram, the connection, the base of Q3, is it connected to the base of Q4 or the base of Q7?
Both. It is connected to both. So we are also going to use current mirror here.
What?
Hello.
Oh, okay. That's cool.
Yeah, I know it's a really good question, yeah.
Sorry, basi umenijibu.
Yeah, okay. Sawa. So aya, you guys are okay till there, si ndio? Okay,
Tuko sawa.
cool. So sorry, my work is a bit messy, but yeah. Aya, so tumeshamaliza na hii side. So let's go to this side. So again, we're seeing the bases here, these two. So tunaangalia 3 na 7. They are connected. So the same base voltage and the emitter voltage pia, it's the same. So we'll apply current here.
Kidogo tu. Tulipata the collector current pia.
Yeah, we were able to get the collector current here. Yeah.
No, not there. Hapo kwa transistor ya Q1 na Q2.
Yes. So we found this is a milliampere, si ndio? Juu hapa tulipata 1 tukasema because of this area thing hapa itakuwa a half milliampere. So the emitter current here will be half divided by 2. So we'll have 0.25 milliampere here and 0.25 milliamperes here as well. But because of the assumption that we normally say that for beta greater than 1, the collector current is approximately equal to the emitter current. So this will be the same as the collector current here.
Thank you.
So we'll use current mirror principle here again. So you check if the bases are connected and if the emitter voltage is the same. So we're looking at transistor 3 and transistor 7. So if that's the case, inamaanisha their collector currents will be the same. But again, remember, the area for transistor 3 is twice the areas of all other transistors. So the current through here will be collector current here, he divided by 2. So it will be 1 milliampere divided by 2. So we'll have 0.5 milliampere here. Okay, so if you have 0.5, to get these two, to get one of these, I just divide by 2. So nitakuwa na 0.5 divided by 2. So my emitter here, which is equals to emitter here, will be, this divided by 2 will be 0.25 milliamperes. Again, it's the same as the collector and here. Are you guys okay till there?
Yeah, it makes sense.
Cool. So we've been able to find our collector current here, 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 and here. So the sum of the currents that are
Wait, Akipole. So is this what Bill was asking about the resistor having a you remember you said that resistor there is it's not there for the second.
Yeah, this one I said.
So is this what Bill was asking before about if a resistor is if it affects a current?
The value of the emitter current. Okay. So Fiona, you okay?
Sijasikia jibu.
Yeah. This is what he was asking, whether the resistors being present will affect the value of the emitter current, which it won't, because current hapa itakuwa same na current hapa.
Okay.
So yeah, having done all that, so sorry, my work was a bit not really well labeled. So let me just take you through. So we have current through 4, 5, 6, 7, which is basically current here, current through transistor. Okay, current 4, 5, 6, 7. These are the ones ukiadd zitakupea current inaingia. So it will give you this nominal current. So we know this is 0.25 plus 0.25 plus 0.25 plus 0.25. So I think you'll have 1 for that. And then we want to look at the nominal current now on the negative side. So yenye inatoka, the ones that are leaving. So the collector current here was 1. So emitter current will also be 1, because we've said for beta, which is much greater than 1, collector current is equals to emitter current. So that is the reason we're using here. So we have 1 ampere here. This was 0.5 on the collector, so it's also 0.5 on the emitter. So KCL, if you add the two, yeah, so current entering is equals to current leaving. We have 1.5 here. Yeah, emitter current is equals to collector current. So if it's 0.5 here, it's 0.5 here. So our negative side itakuwa 1.5 plus 0.5 milliamperes. So this is what I came and wrote here. KCL, but you don't have to write this plus 0.5 to get 2 milliamperes. So nominal current ni hivyo, you get yenye inaingia na yenye inatoka. And normally I think the normally see yenye inatoka it should be more, if I'm not wrong. Yeah, hello.
Yeah,
Hello.
we can hear you, but you got lost a bit there.
You can hear me?
Yeah.
You are breaking for like a whole
I got
minute.
lost where?
You are breaking at the beginning of that sentence where you are saying that usually the current leaving is greater than the current coming in. At the beginning of that
I guess
sentence, you broke.
I got broken.
Yes, you got broken.
But you guys have understood how I've gotten the two, the one entering and the one leaving, Cindy?
Yeah, we can understand.
Yes.
And you understood. And you've heard where I've said that the current leaving, normally, in most cases, normally, to know that your answer is correct, it should be greater than the one entering.
And there's also a question where they were asking why the current leaving is greater than the current coming.
That is something I wanted to ask you guys. Is there, I don't know. I can't.
Why is it so big?
Yeah,
Say
because
because
if
there's
you
a
go back
current
to your photograph,
I go back.
at the beginning of B, the RB. Huko kwa RB, now there is some current coming in from there that isn't part of IN plus. Yeah, there is some current coming in that I1. It isn't part of IN plus, but then we are counting it as part of IN minus. So that's why
Yeah,
the
okay.
current coming out is greater.
Wait, Bill, could you
In
please repeat what you just said?
is
Yeah, the
is
current at RB, at AB, current through transistor at the collector of transistor Q1, that one we haven't counted it as part of IN plus. You see, IN plus when we counted the current through Q4, the current going through the upper transistors. But then, yeah, we only counted those ones. But then now, when we are counting IN minus, this current here also contributes to it. The current through transistor, yes, that one. RB. That current also contributes to the IN minus.
Oh, okay, thanks.
okay with that. And then the last part is pretty easy.
Celestine, I think you've lost your network a bit. You've
Just
lost
what I
your
said in the
network.
beginning. You remember when I said first you check the gain. So it's about
Please start. Mid-band
Your
pote.
network, you lost a bit.
Kama tuna break akisikia tulikaa tumebreak.
Yeah, we can't hear you, Celestine, no?
hello? Hello? Inasumbua.
Hello.
I'm in Russia.
Yeah, hello, now we can hear
Now,
you.
now you're with us.
I'm breaking.
Hello, yeah, we
Can
can
you
hear
guys
you
hear?
now. No, you are back now.
Okay, so
You had broken completely. Hello,
so
yeah, we can hear you.
okay.
Can you hear?
So yes, I can hear you guys very clear. Yeah. So let me start on this part. We want to calculate the mid-band voltage gain, or what we've been calling AD or AV. So first, we realize there are this is a system of two differential amplifiers. So we have a double input. So the total gain for this whole system is this gain times this gain. Okay. So that is why we came here tukasema ndio ya double-ended input, double-ended output, na double-ended input, single-ended output. The difference ni hii ya single-ended output iko na 2. So the first thing you want to do is to calculate RE1. And RE1, we can get it from the formula VT over IE1. So IE1 tulicalculate. So let's see. So IE1 is one of the emitter current, either this one or this one. But usifanye IT, okay? When you do IE1, you do only one. And we got it at 0.25 milliamps. Okay. So we have 0.25 milliamps for our IE1. Our VT, we said it has standard value of 25 millivolts. So just know, if you sleep, when you're eating today, just know VT is 25 millivolts. So our value of RE1 is this divided by this to get that. So if you have RE1, that's cool. So you want to look for RE2. So RE2 near for the double-ended input, single-ended output. So still the same formula, VT over IE2. So let's look for IE2. IE2, sasa we are looking at this other differential amplifier. Wachana na hii ilikuwa ya IE1. So IE2, we'll be looking at emitter current here. And it was 0.5 divided by 2, so 0.25. So 0.25 is our IE2. So again, we have 0.25 over 0.25 to get 100. So our total gain is RC. RC were given as 5,000. Yeah. So RC times RC. So you have 5,000. Yes.
Hebu rudi juu kidogo. Hapo ulikuwa unasema tunatumia IE1 kwa circuit.
IE
Kwa circuit.
kwa circuit.
You were
Okay.
saying. Okay, you see here you maybe IE1 and this is IE2.
I did label it as IE2. Sorry for that.
Okay, so this
I was you to relate it to transistor 2. Okay. But you, just knowing that IE1 is equals to IE2. Yeah.
Okay, so when you are finding this mid-band gain, this what's the voltage gain?
Yes.
So IE1 will only just focus on the IE1, which is the first one, that first system.
Yeah, just this first.
And the other one is the second system.
Yeah, RE2 for this one. Now the emitter will tutatumia ya hii.
Okay, so
make sure because you'll find questions. I've done questions and I've found there are places where this emitter current, this one, will be different from this one. So for the sake of that. Okay, so I think from here applying the formula is not so hard because already we've been given RC, we've gotten our RE1 and RE2. Just remember to put these two here. Don't forget for you to end up here. So are we good with that?
Yes, we can see.
yes.
No, we're good. So I hope you guys have followed. This is a very good question. And by the way, once you're able to do this, the two questions we've done, this is ingine sasa ninywe. It won't even take too much time in them. Okay, so let's go to our third question.
Maybe Celestine, for this one, you can give them an opportunity to try on their own.
To try on their own. Okay.
Yeah.
Okay.
Yeah, like they type out here and then we do.
Is it the same format as the other two?
They're exactly the same.
Okay.
Yeah, actually it is.
Okay, so
let me just zoom in here.
Yes. Nikuulize. Hizi maswali zilitoka kwa pepa?
Kwani zilikuwa zinafaa kutoka wapi?
Okay. Ni vile zilikuwa ngumu before ni attend the session, so utaelewa tu. So, nitakuomba favor baadaye. Sasa wacha tu wafanye maswali.
Okay. How many minutes do I give you guys?
Sometime before 11.
Like 12 minutes to do practice.
No.
10 minutes tops.
Yeah.
I think for first year we can talk.
Eh?
Supposed to do it now.
Yeah. You thought you were going to do it.
I'm here waiting for you to continue, wondering what's the whole.
Because of time, Bill. I'm thinking. Let's use this one. There's a good one. Yeah, there's one I know I can say for you guys for your do it. Yeah, for fun. Yeah.
Okay.
I agree with you. Then maybe we can. I'm not saying, but we can meet tomorrow. I'm not saying we have to.
Okay.
That's just one. I'm on solutions.
Okay.
Wait. Did we just agree we are meeting tomorrow?
No, it's not compulsory. Like
No,
the
but-
last question, she's going to leave it for us to do on our own. And then tomorrow, if you had challenges doing it, you can come and see how it's done.
Solutions.
I'll send a solution, and then if anyone has questions, then I can. Yeah.
Don't send solutions for the last one yet, as in give us time. Because if we are doing the last one by ourselves, okay, me I will just so just
kesho, because ukisema it's open, mtu kama mimi I will feel obliged to attend, and I'm telling you manze, I have to do things to make this session possible. Na nitafeel vibaya. Anyway, sawa.
Okay, it's okay. We'll just find a way. Aya, so let's continue because of time. So I hope you guys have looked at the question. First, you make sure you identify what is going on, and advise you to uandike. You write this is double-ended input. Just write DIDO, as Bill calls it. Yeah, double-ended input, single-ended output. So DISO. Okay, so we're being told the amplifier has parameters of, so the desired parameters are a voltage gain of this. Now remember, because there are two differential amplifiers, this is the product. Okay, this is the product. Always remember that. Kama is mbili, that is something you have to remember. And then input resistance seen by the source is 5. And then maximum output voltage swing is 10 volts peak to peak. So what are we being asked? We're being told, given that the base emitter surface area of transistor 3 and transistor 7 is 4 times that of the other transistors. Again, if you find such a question, if you find such a question and you're being told it's 4 times, write it so that when you're calculating current, you're able to remember. Usifanye mistake and then you don't account for this surface thing. So the base emitter of transistor Q3 and Q7 is 5 and 4 times that of other transistors, which are identical. And the current gain of the transistors is 100. Determine, ignoring base currents. So you see, the way we were saying that the question, most times you'll be told to ignore base currents. So to find resistor RC, so let's start. Here, the total current gain. Tumesema we have DIDO. So for the double-ended input, double-ended output, we have RC over RE times. For the double-ended input, single-ended output, we have RC over 2 RE. Think about this when you're sleeping today. So this is why we're adding up here. So we have RC squared, 2 RE1, RE2. Oh, usisahau hapa RE1, RE2. So the first thing you want to do is to calculate your RE1, which is VT over IE1. So we don't really have anything to lead us to get IE1. So we can look at the question. This question has just been twisted kidogo to there is just a little twist. Because now here we've been given the input resistance seen by the signal source is 5 kilo ohms. So our Z in, you guys remember this formula, is 2 beta RE1. Okay. So the reason why we're using RE1 is because we are dealing with this system. Hapa ndio kuna hiyo input signal. Okay. So ni kama we'll be focusing on getting this IE1. Are you guys fine up to there?
Yeah, it makes sense. Wait, I have a question. RB1 won't come into consideration, or what's it called? Move to the left. That R there, RB. That one won't come into consideration. That one up there.
Who is
Oh, but
RB?
it's not
We are going
considered
to
for
use
the
it.
input impedance. Ah, nice. Thank you.
So input impedance, actually, we're looking at this particular one. We're not even looking at this one because this is where the input equal. So once you're able to find your IE1, then you can find RE. Or you can find RE, then get IE1. So we were being given the input resistance in by the signal is 5. So we know our Z in is 5 kilo ohm. And our formula here, we know Z in, which is 5,000 ohms, is equals to 2 beta RE1. So we can find RE1 from here. If we make RE1 the subject, we divide by 2 beta, divide by 2 beta on both sides. Beta was 100, so if I divide, I get my RE1 is 25. I hope you guys are okay. This is just substitution. So if we get RE1, we can get IE1. Okay. The reason why we want to get IE1 is because, see in our question, if you're able to get IE1, IE2, we can get IT. Okay. If you get IT, you can get, using current mirror, you can get current here. And if you get current here, you can get current here using current mirror, so that you can be able to get IE for this other side. So that is why we're looking for IE. So yeah, begin with that. So applying this formula, RE is VT over IE. Na tumepata RE ni 25. Okay. So IE itakuwa VT over 25. So 25 millivolts, VT is a standard value of 25 millivolts divided by 25. To get our IE is 1 milliampere.
Celestine, I have a question.
Yes.
Concerning the same current mirror thing. You go back to the circuit. You said that if you can find the collector current of Q4, you can find the collector of Q3.
Yes.
And if you can find the one for Q3, you can find the other one.
Yeah, because you see the bases are connected. The base of this one is connected to this one. So their emitters are also connected. So the current, the collector, sorry.
So this connection, but then is it like, are they all mutually connected to each other? Or is it that Q3 is connected to Q4 and Q3 is also connected to Q7, I think? But
Yeah,
Q4 is connected to Q7.
Q4. Sorry, no, come again. Yeah, you're saying this one is connected to this. Yeah, that's okay. And this is also connected to this one.
Yeah.
Yeah.
My question is now, is Q4 connected to Q7? Is the base of Q4 connected to the base of Q7? According to the
I should have never thought about that.
Yes, I think they're all connected to each other.
Yeah.
So does that mean that they all have
or as Michael said in the comments, like they're using jumps and points? Oh no, this is a question. No, I was thinking like they're using jumpers to connect, like from one point they're taking the VB and then they're taking it to all transistors.
Yeah.
So like it's the same.
My question is,
yeah.
So is there a current mirror between Q4 and Q7?
Yes, there is.
Which means that they all have the same collector current.
No, Q7 now has ×4 area.
Okay, but it's like what I'm asking is, once you have Q4, you can just go directly to Q7. You don't have to get Q3 first. If it's the collector Q7 that you're looking for, you don't have to go through to Q3 first.
Yeah, you don't have to. You can go directly because of the current mirror.
Oh, so that's what I was asking. Thank you.
Okay, so I hope you guys are good penye tumepatia E1. So after getting E1 is 1, so we know we have 1 here, 1 milliampere here, and 1 milliampere here. So KCL zikikuja hapa itakuwa 1 plus 1 is 2. So IT will be 2 milliamperes. So if you have 2 here, kuna current mirror between here. The bases are connected and emitters. So if this is 2, this could be 2. But remember, the area is 4 times the area of other transistors. So this one will be 2 times 4 to get your collector current here is 8 milliamperes. I hope you guys are good with that one. So if you're able to find that, okay, I don't know, but I'm really used to doing this. Yeah, so just bear with me. This is times 4. The base of this one is connected to the base of this one. The emitters are also connected. So the collector here is same as collector here. And because this is times 4 and this is times 4, then this will also be 8. Because they have the same area. So if they have the same area, the collector current will just be the same. If they have different areas, we put in the factor of the area. Yeah. So are you guys fine up to there?
Yeah, I think we're okay.
Okay.
Yes.
So again here, same thing. Hapa sasa hata hakuna shida because now when you have 8 here, divide by 2, you have 4 here. 4 here. Okay. So we know our IE is equals to IC. So IC here will also be 4 milliamperes. Okay. So to look at tumeulizwa nini? We've even gone far. So we wanted to look for IE here. Yeah. So the reason we wanted to look for IE is so that we use it to find RE for the second part. So RE is VT over IE2. So we have VT is a standard value of 25 millivolts divided by 4 milliamperes to get 6.25 ohms. So we've gotten RE1, we've gotten RE2, doi. So for us to get RC, tutaingisha tu sasa value zetu hapa. Again, we were told it's 12,800 times 2 times RE1, which was 25, I think, 25. RE2 is 6.25. RC is 2 kilo ohms. Are you guys cool up to there?
Yeah. Okay. Wait, but first of all, that formula for RC squared, it's which one you've manipulated?
It's this one. It's this one actually. It's
it's
this
that one.
Yeah. I've just
Okay.
nimezileta tu on one side. Yeah.
Okay.
Ndio nikaenda na hii.
Sawa, thank you.
Okay. So I hope you guys are following. Power supply. Where do I go back? Fiona?
Gosh, I'm saying yes, we are.
Oh, okay. Sorry. So now you want to look for power supply.
Please go back to that. The same question Bill was asking.
The same question. How I've manipulated the formula. Yeah?
Oh, okay. Yes, now
Hello.
I think it. Nico.
You understood?
Yeah.
Okay.
Yes, I have.
So let's do, we want to look for power supplies VCC and VEE. Okay, so we can get VCC by saying VCC is equals to the drop here. So kutakuwa na, I don't call it IC, should I call it? Yeah, IC RC plus VC. Single. Hope you guys remember that. Yeah. So VCC is ICRC plus VC. Yeah. Now we remember that for VC, we said, now in this question we've been told the maximum voltage swing is 10 volts peak to peak. So how do we find VC? So VC, just from this statement, you should be able to remember that VC is 10 divided by 2, should be more than half. So we add 1 to satisfy that condition for more than half. So 5, 6. Okay. So VC will be 6. So that is how I found my value of 6. From what I just said, that VCC is equals to IC RC plus VC. If you make VC the subject, we'll bring this one here in a negative, so VCC minus that one. So we have VC, we have IC. IC, we got it as 4. We have RC, we calculated RC and got it as 2 kilo ohms. So we have 4 milliamperes, 2 kilo ohms, to have 6 volts and 8 volts. So again, normally the magnitude of VCC and VEE is the same. But here we got 6 plus 8 is 14. But there's something the lecturer once said when we were doing such a question, is that there are particular standard values for voltage. VCC and VEE you can use. So kama umepata 14, you'll round it off to a standard value. Like now here we chose plus and minus 15 volts. Okay.
Celestine?
Yes.
Can you take me back to the group? So, in the diagram, hapo kwa V in. Suppose we had a resistor from hapo to hapo, Z in done for the input resistance sent by the switch network will be Z in parallel to now that resistance.
So you're saying Z in, we'd have Z in.
Yeah.
So we'd have Z in is 2 beta times RE. But if we were talking about, I think this is normally R source. Sure. There's something we talked about, Z source being R in, or Z in, and parallel with Z, or R in parallel with R. So we will look for R in. Okay? R in is Z in, sindio?
Yeah.
2 beta RE. After you find the value of this, you'll do this value in parallel with the value of the resistor.
Oh, okay. Like the value hapo for 5 kilo ohm will add like and RS, and it will be add Z. So it's the add in.
This is by the way, this is RS. This is
That's RS?
Yeah.
Oh, okay.
But now because we have no resistor, then you see it would be now R in parallel with R, but there's no resistor, so itakuwa to R in. Ndio maana tunatumia 2 beta RE.
Okay. Thanks.
Okay.
Celeste.
Yes.
Celeste, I can't hear that mostly. Please repeat her question and the answer.
Oh, she was saying.
Kindly, please.
Okay. You can hear me, yeah? Hello?
Yes, I can hear you.
So she was asking if there was a...
Yes.
So you guys remember there was the previous question, I think we had a resistor. Where is this one? This question. Nice. In this question we had a resistor. Okay. So our R or our Z, our impedance in by the signal, tunasemanga normally ni R in parallel with this resistor. Okay. So she was asking if we have a resistor, how we would calculate the value of so. But now you see in this question of ours, we don't have a resistor here. So, because we don't have a resistor, we won't even do it in parallel with anything. The resistance being seen by the source is equal to the input impedance. Fiona, you okay?
Yeah. Now, if we go back to where you were saying 14 is approximately equal to 15. So now that final answer will be 15, Amma?
It will be 15. We were doing this
because of the...
Conventionally, we do not have a rating. We don't have a power rating of 14 volts. I think it's either 15, I think we have 12. I'm not sure we have 10, but I know we have 14. We have 15, 12. The other ones.
So how do you know it's approximately equal to 15? Because I'm saying that's a whole voltage. As in, sa ukipata 10 unaweza sema it's approximately equal to 15.
It's about 12. But I'm not sure
Ama
if 10 is a standard. I should Google. But I know 12. Like if I calculated and got 11, I would say 12.
Okay.
If you've noticed, ever since
Okay.
we're doing analog, values it with the VCC na VEE. Mostly inakwanga 15, ama 12. I'm not so sure if you've used 10, but you've realized we don't use, hatujaitumia 11, ama 6, you get. Because there's a particular convention.
Okay. So thank you.
I think I could I'll research on the conventional values of power that we should use. Okay. So we are on to the last part of the
Celestine,
yes.
if you just put your camera over the diagram and let it cover the diagram. So the rule is that RC should always be the same for all the amplifiers.
Yes.
That's the rule.
Yeah.
Okay. Good.
Cool. Okay. I hope you guys are okay. So let me take you through the last one. So value of bias resistor, RB. So RB, Bill, ndo hii RB yenye ulituuliza. We are going to do this.
Okay.
So here, VCC, kiona penye tunatoka. So this is the path you're following. So this is like the loop we're using. It's like we're using the outer loop. I don't know how to call it. So we start from VCC. So you know VCC will be equal to the drop here plus the drop here and equal here. So tuko na VCC. This was I1 tulipata kama 8. So let me write it somewhere so that you guys see. So you have VCC plus the drop here. This is I1 RB plus the VBE here. So VBE plus minus VEE. Okay, this should be equal to, sorry. So VCC.
Wait, Celestine, I think I have a question. There you have disconnected the connection between the VCC, that line there.
It's actually supposed to be there.
Or it's supposed to be there, okay?
Yeah.
Or my question is gone.
Okay, cool. Fuchs. Yeah. So I hope you guys are understanding where I'm coming up with this thing. So we are saying tumeanzia VCC. Okay. So tunakuja, there'll be some voltage drop here. There'll be some voltage drop here. And tutakuja tumalizie na VEE. It's a negative value. So VCC is equals to I1 RB plus VBE plus minus VBE. VEE, sorry. Hope you guys are fine with that.
Yeah.
So let RB. We already got I1 as 8. So this is sorted. We've got VCC as 15. We know VBE is 0.7. VEE is 15. We're as well done with this question because now we just make RB the subject. So we make the RB the subject. We'll have VCC plus VE over minus VBE over I1 for me to get, I think this is straightforward for you to get 3.66 kilo ohms. Are you guys okay with that? Actually,
Yeah.
okay.
If we go to the circuit, so the page. So if we choose any other loop, it will get the same answer.
If we choose any other what?
Loop.
Loop.
Like if we
should.
Yeah.
I believe it should.
You know how you took the outer loop?
Because the outer loop had RB. And this is what we're trying to look. Hello? And I feel like it's a pretty straightforward loop, yeah? Yeah, it's relatively pretty straightforward. Okay. Sawa. So I hope you guys, because you're done with this question. Hii tumemaliza. We're done. So I think the next one will be really easy for you guys because it has only one amplifier. So it will take a few minutes and we'll be done. So let's go through it very fast. So let's study our diagram. So here we have a double-ended input and we have a single-ended output. So automatically we know that our gain will be RC over 2 RE. Yeah, I think pretty much. Okay. So we're being told figure 1b shows a differential amplifier circuit with a gain of 150. So this is voltage gain. And make sure you don't confuse voltage and current gain. Normally, he'll label current gain as HFE. So the transistors used have a current gain of 100 and RB of 10 kilo ohms. If the input resistance seen by VI is 4 kilo ohms, determine the collector resistance RC. Okay, now this is pretty easy because we know we can get RC from this formula. So from this formula we know.
Celestine, I think you're hanging a bit.
So let's find RE. Sorry? Nianze tena miski?
Ulikuwa umepotea kidogo.
Okay. Oh, sorry for that. So you've seen our diagram to a double-ended input and a single-ended output. So our formula for gain will be RC over 2 RE. So our first question is asking us to find the collector resistor RC. So RC is equals to the gain times 2 RE. So tunaishia hivyo. So first we want to find RE ndio tuipoxia hapa ndani. Okay. So how can we find RE? Oh, quick. In our question, let's see tumepewa nini. We've been told the resistance seen by VI is 4 kilo ohms. So we know that, let me call it our Z in to be RE. It's 4 kilo ohms. So 4,000. So for me to get RE, I'll have 4,000 over 2 times beta yetu ni 100. Okay, so our RE will be 20 ohms. So sweet. We have RE 20 ohms. Our gain is 150, so it's just one transistor. One differential amp. Okay, I think we started. So to find RC, it will be our gain 150 times 2. RE is 20 times 20. That should be able to give you 6 kilo ohms. Are you guys okay till there?
Yeah, we're okay.
Cool. Okay. So I hope you've seen how you'll get RC. And then the next one, power supply VCC and VEE. We need to find our power supplies. We need to be able to know our VC. Okay. So to find our VC, lazima we find our current. So you have to find the collector current here, so that you're able to find emitter current and collector current here. So let's see what we're going to use. Nice. We know that RE, I'm just going to write here. So we know that RE, I actually wrote it here. We know that RE is VT over IE. Now this is the IE we're dealing with, again, remember, E2 here, which is equals to this one. So they're the same, this and this are equal. So RE is equals to VT over IE. You can get IE, because you already know RE is 20. So 20 is VT, which is 25 over IE. So IE is going to be 25 divided by 20 to get 1.25 milliamps. So the current flowing here is 1.25. Current flowing here is 1.25. If you do KCL, yeah, we get that the tail current is 1.25 plus 1.25 to get 2.5 milliamps. Now, we'll use current mirror because we are seeing the bases are connected and also the emitters are connected. So same voltage on the base and emitter. So knowing that the collector current here will be the same as the collector current, because we know the collector current have same collector current here. So if this is 2.5, this is also 2.5. So I hope you guys are clear till here. Are you okay?
Yeah, you're quite fine.
Okay. Sijakatwa na waves. Haya. So with that, what was I even looking for? Oh yeah. So we're able to find our IE is 1.25. IE is equals to IC. So IC, or what I'm calling I1 in this case here, is simply 1.25 milli. Well, what are we looking for? We're looking for VCC and VEE. So VCC is equals to drop here plus VC. So I used I1, so I'll say I1 RC plus VC. So I1 RC plus VC. Okay, what do we need to know here? Okay. Now, I can't use this formula because I can't find VC. The reason why I can't find VC is because in the question, we've not been given the maximum voltage swing peak to peak. So we'll use another formula. We'll use another method rather. So we'll use this path. So we'll say VCC is equals to the drop here. So from here we'll say VCC is equals to let me call this I1, I1 RB plus VBE, so this VBE plus VEE. So this is what I actually wrote here. So VCC is I1 RB plus VBE minus VEE. So with that, we have VCC and VEE will come on one side, I1 RB, VBE. We have the value of I1 as 2.5. We have the value of RB as 10. So we'll have 2.5, 10, VB 0.7. Now this is somewhere I want you to be very keen about, because we normally say the magnitude of VEE is equal to the magnitude of VCC. So I can as well say this is 2, the sum of these two is 2 VCC. Aya. Nani ako na swali hapo? Hello.
Yeah, sidhani tuko na swali hapo.
Udhani uko nayo, si ndio? So I hope mumeona mbona nimetumia 2 VCC hapa, kwa sababu magnitude ya VCC is equals to magnitude ya VEE. Okay? So I've just come and say 2 VCC to accommodate for the VEE. So that if I'm able to find VCC, divide this term by 2, VCC is equals to VEE is equals to 12.85. And because this is not a standard value of VCC and VEE, I've rounded it off to 15. Because 15 is a standard value. Okay. Questions, people?
I think hapo kwa loop mi nilianguka kidogo.
But sahi uko
Why
sawa.
were we using that loop badala ya hiyo method ingine?
Which method?
Hiyo ya VC, VCC.
Okay. Yeah, kwa sababu unaona hatuna VC. Si ndio? Kwa sababu tungepewa bidii kwa swali tungepewa maximum peak to peak voltage tungetumia hii very easily.
Yeah.
But sasa we've not been given, so we can't find VC. So we are at a dead end hapo.
Oh.
Unaona?
Yeah.
So nikasema sinipite hivi basi.
Oh, so you take that loop instead.
Oh,
sawa.
Okay.
Alafu Mike uko na swali hapa anauliza why don't we take 12 na 12 is closer to 12.85?
In practice, we will round it off. Okay, we will round it to a higher value, not a lower value than what we've gotten. Kwa sababu tukiround to a low inamaanisha si basi maybe hata I don't know. It won't meet the power qualifications, I don't know, criteria. But normally from the questions we've done, we normally round it to a higher value, not to a lower. Kama tungepata 11.58 tungeweka 12. But sasa now between 12.85 the next highest value is 15. Mike, I hope I've answered your question. And then, okay. So we are on to the last question, which I believe is the last part of the day. So maximum voltage swing, peak to peak. So we've already been able to get, sasa hapa ndio tutatumia hii. Si ndio? Because tumepata VC, tunajua I1 ni 1.25, tunajua RC, tunaweza pata VC. So VC itakuwa VCC minus I1 RC. So I came here, VCC minus I1 RC, 15 minus I1 ni 1.25, RC ni 6. So I got 7.5. But remember that we said that VC should be more than half. So V peak max, V peak to peak inafaa kuwa peak to peak max over 2 plus 1. So for me to get V peak max from VC, nita minus 1. So if my VC was 7.5, I'll do 7.5 minus 1 to get 6.5. Then I'll multiply by 2. Okay. So 7.1 minus 1 to get 6.5 times 2 to get 13. So this is our full swing. Okay. Again, do not confuse maximum voltage swing with E value of VCC. You usikuja round off useme 15. This is the swing. This is not the value of VCC and VEE. Yes.
Okay.
Yeah. So I think I have finished. Is it 10 minutes to time to open for forum for questions?
Let's
Is
ask
Bill
Travis.
supposed to
Travis.
present something?
Sorry?
Did Bill have plans of presenting anything? Or this was a combined effort?
It was
Celestine was presenting.
but he's going to take us through the second part.
The
What?
second?
Which part? No. We were doing question with Celestine. It was doing the
But it
presentation.
was coordinated though, yeah. It
What? Okay, so
I'm not doing any presenting. Celestine was doing the presenting. Yeah.
okay, but your contributions tonight have been much appreciated. I believe.
Thank you.
Okay, are there any other presentations that will be carried out? Or because it's 30 minutes to time, and you guys may or may not have questions. So,
There are guys.
is it?
Hello?
Gisheru, you're breaking a bit.
Yeah.
I'm breaking.
Yeah, you okay.
I'm asking.
Celeste,
Yes.
wewe kunywa soda gani?
Mimi.
Mm.
Yoyote zote tu, lakini napendanga passion.
Endelea kunywa na usiwache.
Carefully.
Haya. So naona Fiona is typing something. Travis, it's your time. Celeste, help Travis. Travis ako wapi? Hello? Situna is asking why I'm not rounding off the full swing. No, okay. You can get pretty much any value for swing. Yeah, I can't say there's a standard value. It's like, how do I say? You see the way we say we step down from 250 to 111, and so you get like their standard values we normally use. Like let's say, does it explain aje? Wow.
Ni kama resistor.
Ni kama resistor. Okay. Another you can say battery. The battery is of particular ratings. Yeah. Unaweza pata ya 5 volt. Unaweza pata maybe, I'm just putting an example, like standard, how they manufacture batteries is what I manufacture either a 5 volts, ama 250 volts, ama 110 volts, but they'll not necessarily do 108 volts. So if I want to have 108, I can order a battery that is rated 110. Yeah. Okay, just in layman's language, that is what I mean. Okay. I don't want to talk longer. Yeah. I'll send a question to the group for you guys to try. It's a very straightforward question. And if you go through this question, tuseme mara mbili, wewe ende ufanye exam hata sasa, what are you waiting for? Situna, I hope you've gotten the answer you wanted. Oh, you guys are so sweet. Oh, thank you so much. Thank you. Oh.
Just don't cry though. Anyway, I wanted to please ask you, ukituma hiyo swali, usitume solution immediately.
Okay.
Like you can send it after some few hours.
No problem. Okay.
Yes, yeah.
Okay. Yeah. That was the last question I sent. It wasn't done well. There was someone, the person who did it didn't do it well. So I need to correct it. So please don't refer to CAT 2017. I'll do it again. Or yeah, I should give you guys the question. Yeah. Actually, you guys, this is the question you'll do because it's exactly what we've been doing. Yeah. So I think Gisheru can take over. I think my presentation is over. Gisheru.
Right. Can you guys hear me now? I was breaking a few minutes ago.
Yeah, we can hear.
Yeah, okay.
So, okay. First of all, thank you, Celestine, for this amazing presentation. I think most, if not all of us, have some newfound hope in analog electronics, myself included, very much included. And well, that was a lot of work, it looks like. It was a lot of work, and yeah, we're very grateful for your efforts and for helping all of us. I'm sure for a lot of us, this would have taken much longer. Okay, for me, anyway, it would have taken much longer. So yeah, thanks from me and from everyone else in attendance. Okay, so well, since I'm gonna guess that there are no further questions as far as analog electronics is concerned for tonight, and I don't know what you guys were feeling towards the suggestion of having an optional meet tomorrow in case any questions arising from the question that's been posed to us come up. Maybe we can do some sort of vote or something. I don't know. Because, well, if the number of people who are for that idea are very small, perhaps you could just contact Celestine
Yeah, I
personally.
take it back because I've realized it might be a lot. So I take it back.
Or maybe we could have a discussion via WhatsApp.
Yeah, that could work because,
like we say, between now and tomorrow 9 p.m. don't ask about that any question related to that question that she sent us. And then now from 9 p.m. if you have questions, just send. She answers them.
yeah, that could work. I think that'd be very, very flexible for anyone who is concerned or anyone who has a question. Like, there'll be no obligations. Joseph, I'm looking at you. There'll be no obligations to attend anything. Yeah. So, yeah, if any questions arise from that.
Fiona, you can stop recording.
Oh, yeah. Okay, I forgot to stop recording. Sorry.